I'd like to describe section 13.2 on coloring graphs with two colors. Pretend you have 6 children, Al, Bob, Chris, Dee, Eve, and Faye, or A, B, C, D, E, and F. And some of these children like to fight with each other, as represented by an edge. So for example, this edge represents that Al and Bob like to fight, whereas the absence of an edge here represents the fact that Al and Chris don't like to fight. They get along just fine. And now you have 2 rooms, and you'd like to put your children into these 2 rooms such that no fights will break out. So you don't have 2 children who like to fight in the same room. And you ask, is it possible to divide these children into rooms satisfying that constraint? It turns out in this case it is possible. So down below, I've drawn my children in rooms 1 and 2. So we have B, F, and E in room 1, and A, C, and D in room 2. And all of the edges are between children in opposite rooms. So all of the pairs of children who tend to like to fight with each other happen to be in different rooms. So we've succeeded. Our children are happily arranged into 2 different rooms in a manner in which they won't fight. Let's rephrase this task in a more graph theoretic sense. So you could rephrase this as, given a graph, can you color the vertices of your graph with 2 colors, lighter and darker, such that adjacent vertices don't have the same color? So in the picture above, we have colored our graph with 2 colors. All the vertices on the left are with the lighter color, all the vertices on the right are with the darker color, and adjacent vertices connected by an edge don't share the same color. Looking forward, in sections 13.3 and 13.4, we'll consider problems of this form not with 2 colors, but with an arbitrary number of k colors. So you could think of this as you have many more children, you have 20 children, and you want to divide them, say, into 3 rooms or 4 rooms, such that children in the same room don't fight. 3 rooms would be the analog of 3 colors, and 4 rooms would be the analog of 4 colors. Another name for such graphs is bipartite graphs. So a graph is deemed to be bipartite if you can divide the vertices of the graph into 2 sets, such that no edges exist between 2 vertices of the same set. So here we've divided our vertices into 2 sets, room 1 and room 2, where no edge exists between 2 vertices of the same class. I'd like to recall Theorem 13.1.1 from last section, which says that if you draw circles in the plane, then the regions produced by those circles can be colored with exactly 2 colors so that adjacent regions don't share the same color. This can be rephrased as stating that a particular graph is 2-colorable or bipartite. So which graph is this? This is the graph that I've drawn here on the right. So for each region, we have a vertex in our graph, and whenever 2 regions have an arc, share an arc in common, then we connect those 2 vertices with an edge. And here you can see that we've colored this graph based on whether the region is inside an odd number or an even number of circles. So in this coloring, the darker vertices are regions that are in an odd number of circles, like 1 circle or 3 circle. Whereas the even vertices, the white vertices, are those vertices that are in an even number of circles. So here this vertex is inside 2 circles. So we're going to now abstract away from children fighting and just ask, what graphs do we know that are 2-colorable or not? So this first question, what graphs do we know are not 2-colorable? Well, any graph containing a triangle is not 2-colorable. You're going to need at least 3 different vertices, 3 different colors to color the adjacent vertices with different colors. And so continuing on top of that, whenever you have the complete graph on 3 or more vertices, then that complete graph is not going to be 2-colorable. A better necessary condition for a graph to be 2-colorable is that any graph that's 2-colorable better not contain a cycle of odd length. So here we have some example cycles of odd length, length 3, length 5, and length 7. No such cycle can be colored with two colors, because if you start with red, blue, red, you're going to have two adjacent red vertices. Or in this 5 cycle, if you start with red, blue, red, blue, red, you're going to end with two adjacent red vertices. And same for the 7 cycle, or a 9 cycle, or an 11 cycle. So in order for a graph to be two colorable, it better not contain any odd cycles. What's remarkable is that this necessary condition is also sufficient. So this is the content of Theorem 13.2.1. A graph is two colorable if and only if it contains no odd cycles. All right, so if it's two colorable, then it contains no odd cycles. That's not so hard. But what's surprising is that also, if it contains no odd cycles, then necessarily we can color it with two colors. Let's discuss the proof of this theorem. One direction is easy. So if a graph is two colorable, it can't contain any odd cycles. That's simply because an odd cycle, as we discussed, is not two colorable. For the reverse direction, going backwards, we need to prove that if our graph has no odd cycles, then we can color it with two colors. This is a little bit more difficult, but let me explain the algorithm for doing this, or for seeing this. So how we'll begin is we'll pick an arbitrary vertex A in our graph, fix this vertex A, and color it red. And now we're going to continue coloring all the neighbors of A. We're going to spread out from A, coloring more and more vertices in this graph. So take A, color it red. All the neighbors of A, color them blue. These 3 vertices right here. And now all the neighbors of those vertices that are yet uncolored, so this vertex, and this vertex, colors them red. I forgot this vertex here should also be red. All the neighbors of those vertices that are yet uncolored, color them blue. So this vertex, and this vertex will get colored blue. All the neighbors of those vertices that are yet uncolored, color them red. This vertex right here will be colored red. So that's how we're going to color our graph. Take an arbitrary vertex A, color it red, and then as we spread outwards and further and further outwards in neighborhoods, alternate between red and blue colors. And now we claim that if this graph contains no odd cycles, then the resulting coloring is a proper coloring. No two adjacent vertices have the same color. Okay, so let me prove for you that since we have no odd cycles, the resulting coloring is a good coloring. So suppose for a contradiction that we had two adjacent vertices, u and v, as drawn here, of the same color. What we'll do is we'll take a shortest path from u next to our starting vertex A, and a shortest path from v back to our starting vertex A. And you'll note that colors alternate along these paths. So if u is blue, then as we follow the shortest path back to A, we go blue, red, blue, red. And if v is colored blue, then as we take the shortest path from v back to A, we alternate blue, red, blue, red. Now, look at the first time that those paths from u and v back to A merge. They might not merge until you hit A, or they might merge slightly prior to A, as we see here on the right. In either case, consider now the cycle that goes from u towards A to the first merge, and then from that merging point to v along the shortest path, and finally crosses the edge from u to v. So consider the cycle that goes from u to the first merge, and then to v, and then that crosses the edge straight from v to u. This is a cycle of odd length. The reason why it's a cycle of odd length is that the number of steps from u to that merge vertex is the same parity as the number of steps from v to that merge vertex. In either case, it's both an even or an odd number of steps. Okay, so as I go from u to the merge vertex all the way back to v, I've necessarily traversed an even number of steps. And then I add in one more edge into the cycle to get a cycle of odd length. So if this coloring were not a good coloring, then we would have an odd cycle, a cycle of odd length. Therefore, since our graph has no cycles of odd length, this coloring that we've produced in the algorithm drawn above does give us a proper coloring of the graph with no two adjacent vertices of the same color. This completes the proof of our theorem. A graph is two-colorable if and only if it contains no odd cycles. I'd like to end with a few remarks. So first of all, our proof shows that there's only ever two colorings for a graph. So if a graph is two-colorable and it's connected, then there's precisely two colorings of it. Vertex A, you could either start with red, and then that fixes one possible two coloring, or vertex A, you could start with blue, and that's the only other possible two coloring. What's nice about the proof of theorem 13.2.1 is that it gives us a fast algorithm for deciding if a graph is two colorable or equivalently if it contains any odd cycles. Simply start at an arbitrary vertex A and color it red, and then expand out, coloring the neighbors blue, red, red. And if that algorithm works, the graph is two colorable and has no odd cycles. If that algorithm doesn't work, then the graph is not two colorable and does have odd cycles. Exercise 13.2.1 states the following. Prove directly that the graph obtained from regions formed by circles in the plane contains no odd cycles. So here we have regions in the plane formed by drawing circles, and we want to prove that the resulting graph drawn in red, with one vertex for each region and with an edge connecting adjacent regions, has no odd cycles. Now, one way to prove this theorem would be to use prior results. We proved in theorem 13.1.1 that this graph is two colorable, and then in this most recent theorem 13.2.1, we proved that if a graph is two colorable, then it contains no odd cycles. Therefore, this graph in red has no odd cycles. However, let's also give a direct proof. Okay, so I have my graph drawn in red, and I want to prove that there's no odd cycles. So pretend I walk around a cycle in this graph. Maybe I started at the vertex at the top, and I walk all the way around this outside triangle. Okay, I want to prove that the length of this circuit that I've done is even. The way I'm going to observe that is that you'll note each edge that I cross corresponds to crossing the boundary of a circle. So this edge that I cross corresponds to crossing the boundary of the bottom left circle. This edge that I cross corresponds to crossing the boundary of the top circle, etc. Every edge that I cross is when I cross a circle. Now, when I walk around in a loop, I'm going to cross any particular circle an even number of times, just because I need to keep alternating between inside and outside that particular circle. So for example, let's consider this tour that I discussed, starting with the top vertex, and I walk around the triangle once. How many times do I cross the top circle? Well, I cross it once here when I go from inside to outside, and then I cross it once more here when I go from outside back to inside. Okay? So if I start inside a circle, I'm going to cross that circle an even number of times to end up inside that circle. By contrast, if I consider the bottom left circle, I start outside that circle, I'm going to cross that circle an even number of times to end up back outside that circle. Every circle gets crossed an even number of times, and therefore, since every edge corresponds to crossing a circle, we've seen that this loop necessarily crosses an even number of edges. It's an even cycle, not an odd cycle. Thanks.